So this is our intro video to finding volumes of solids. So what's going to happen is we're going to rotate our function about a given axis, and the first one about the x-axis. And what it's going to do is create a solid. But this is called the disk method because that rectangle that we always draw is going to be creating a disk. So just to give you an idea of what we're going to be doing, we always take our function and graph it. So we graphed it f of x equals x squared from 1 to 3 right there. And then we have the area under the curve. So we draw our little rectangle here, just like that. And so we would use that rectangle as our reference. And so obviously it has a thickness of dx, and it says y equals, and everything is great because we have x squared here. That's what we're looking for. But then we're going to rotate it. And as we rotate it, what it will do is create these disks. So it looks like this. So here's our shape, and we're going to rotate it around. So it does this. And it's really hard to see, but I'll show you another picture. So as we rotate it, that purple thing becomes this. So you can see it here being rotated, still the same thing. But now if I grab it and move it forward, you can see what shape did it make? It's a disk. So this solid that it's creating looks like that. And by rotating the rectangle, it makes a disk. So what it basically is that rectangle is the radius. And what we're going to do is this. That one rectangle is actually going to be an infinite number of rectangles. So if you remember, we're going to take the area from this case, from 1 to 3. So when you do that with the integral, it's going to not just make one rectangle, but all the rectangles through the whole thing. So it looks like this. As it moves through from 0 to 3, we're moving that rectangle through the whole thing. And so it looks like this with our basic function. But after we've rotated it, it's made our solid. And those rectangles just become, trying to get it to where it's perfectly centered here, our circles. And so you can kind of see it as it moves. So as that radius, that rectangle moves through our function, as the x goes from 1 to 3, it's going to create every single circle, thereby filling in our solid. So our first rectangle at 0, if you were to plug 0, our first one is at 1, we would get an area of pi. But remember that thickness here is dx, so it's a super, super thin rectangle, so it's really just pi dx. And so as we go through this entire thing, it's plugging in 1, and then 2, and then 3, and then 4, and then 5, through all of these, filling in the entire thing. It's giving us the area of these very paper thin circles. And so that's why we're using a dx. So if you use a dx from 1 to 3, it's going to plug in 1, 1.1, 1.11, 1.111, and so on. Every single number possible between 1 and 3, filling it in. So it's just doing this. So when we take our integral of a dx, it's just going to go through and give us our exact solid. So if you can find just that one shape, then all you have to do is take the integral of that shape with a thickness of dx, and it's going to give us our volume. So that's the main idea of this section. So as we rotate it, it gives us our circle. So there is our rectangle, and we now are going to call this our radius, right? And our radius here, though, is y. So if you look at our picture up here, I've already labeled it as y, which is x squared. So that is our radius. And then what are we doing? We're rotating it. So what is the area of any of these circles then? Well, it's pi r squared. And in this case, our radius is x squared. So it would be pi x squared squared. So our area here is pi x to the 4th. So now you can find the area of every single rectangle. So as we move through here, that area will give us the area of every single one of these disks. So pi x to the 4th is all of these areas. So if we got to the very end, which is 3, plugging that into our formula, we know that last disk has an area of pi 3x to the 4th. See, if you were to plug 3 in, you would get 3 squared, which is 9. So our radius here is 9. And so that's pi r squared. So 9 squared is 81. It'd be pi 81, which is what we have here, 81 pi. But now each of these has a thickness of dx, so when we convert them into volumes, we're going to multiply them by dx. So we end up with this nice little formula here. Area, and since we're making discs, we can actually change it into start to finish of pi r squared dx. And now, obviously, r here is going to be in terms of our y, which is our x squared, and we're going to be modifying these a lot more, and there's going to be other situations. So it's a very general formula right now. But let's try it. So now that we've looked at our picture up there, we know that our area, right, this is our radius. So we know that we're going to go from 1 to 3. And then our area goes inside dx. And what was our area? Our area here, we always want to write off to the side, is a disk. So it's pi r squared. Looking back at our disk, our radius here is x squared. So we would write pi x squared squared, which we did above, which is pi x to the 4th. So now we know our area. We do 1 to 3. Pi x to the 4th dx, and what this will give us is that solid. It'll give us the volume of that solid. So this is going to take it, the way I like to look at it, is the area of that one disk is A, its thickness is dx. So now we have found the volume of just that one paper thin disk, and what it's going to do now is add up every single paper thin disk from 1 to 3, as it again translates through our function. So I love this picture, so I have to keep going back to it. So you can see it just go through the 1 to 3. All of these have an area of pi x to the 4th. That's pi x to the 4th with a thickness of dx. And it's going from 1 to 3 to add them all up. So that's what our integrals here is doing, is it's summing them up. So if we plug this in our calculator, we get 48.4 pi, or 152.05. And there you have it. So that is the volume of that solid that was created. So that one that we just made, this one, so it kind of looks like a curved cone with the tip cut off. That volume is that. So that means our volume here, you can see it now as the limit as n approaches infinity from I to 1, from I equals 1 to n of our function a of x of I. So remember, it's plugging in x to give us the area of each of this disk. So this right here is the area of one disk and how thick the disk is. That gives us that one volume, and then we add them all up to get the total volume. So this becomes the integral from a to b of a of x dx, which is what we're talking about here, start to finish area dx. There you go.